All right, so for this, this is kind of like a bonus lecture. Just didn't feel like we covered quite enough to fully prepare you for the exam, so I just wanted to go over some more examples. So this is the second exam two, so exam two number two, solutions. So for this problem, looks like another Weibull distribution. Okay. Don't think this is the same. No. Okay, so calculating the CDF, again, we should understand, well, you should hopefully understand what the CDF is, right? You don't want to spend your time looking certain things up. Hopefully you just have known by now. So integrate from the lower bound to T, I'm calling it, of the PDF. And to do that, we need to use U substitution, uh, setting U equal to the exponent of E, except for the negative sign, and making sure we change the bounds of the integral. And pretty easy integration after that. Survival function by definition, 1 minus the CDF, pretty easy. Hazard function by definition, PDF little f divided by the survival function. Another conditional probability, lasting at least 10 years, given that it lasts at least 5 years. Same setup, using regular probability rules. Simplification, lasting 10 years implies that it lasts 5 years. And so it looks like this. And so we can just plug in 10, S of 10 divided by S of 5. Just plugging 10 and 5 into there. And we're done. And so does it appear that the part becomes more or less likely to fail? So that's kind of directly, we should immediately know we are wanting to use the hazard function for something becoming more or less likely to fail. Right, becoming more likely to fail is equivalent to becoming weaker in terms of a hazard function. So that would be an increasing hazard function if that was the case. So it's pretty easy to take the derivative of this, right, and see that it's positive everywhere, right? It just becomes 2 over 25. And so the hazard function is increasing, and thus the part, or whatever we're talking about, becomes more likely to fail and becomes weaker. Okay. Likewise, if this was negative, well, taking the derivative, if it was negative, then it would be a decreasing hazard function and less likely to fail. If there was no t in this hazard function in h, then h prime would be 0, and it would be a constant hazard function. And so again, because this is a Weibull distribution, we can look and see that alpha is greater than 1, and so it's an increasing hazard function and becomes more likely to fail. Again, alpha wasn't specified, right, but we can tell that this looks like a Weibull distribution, and it is, right? This is alpha t to the alpha minus 1, and again, alpha's here, so alpha is 2. Okay, another data analysis, reliability analysis example. This time we've got 1,000 rods, and the data is the difference between the desired length and the actual length of 1,000 rods. And so it's stating that a negative value would indicate that the rod is too long, and a positive value would indicate that the rod is too short. Okay, so desired length minus actual length. And again, we have some analyses here. That's how it would have looked, but now you just have this data set and you can figure this stuff out for yourself. Of course, these sorts of things aren't really as useful to us because we don't have to do this sort of thing by these intervals by hand. Although for some of these you could, but again, probably not the easiest and quickest choice. So which model do we prefer? Looks like, again, we're skipping out on the exponential. That could be a possibility for your exam though, but for now we want Weibull, normal, and gamma. And so I would say one of the things is, based on the wording of this question, oops, okay, wrong one. Based on the wording of this question, it might be a little confusing as to what it is that we're doing. So we're taking the difference between desired length and actual length, right? But there's not two groups, okay? It's desired length is just a number, right? And we're just subtracting what we actually measure from the desired length. So this is actually only a one sample problem. Okay, and so you didn't really get that from this, right? You'd have to kind of logically determine that. However, based on the data, what are we talking about? Rods. So rod, so we need, of course, you can download that. That was on the last email that I sent before, right before the previous lecture. So we need rod, we need R, of course. We still need pretty much everything else. Our Weeble analysis code, rod, and again, I'll keep it as data so I don't have to change this code so much. Oops, change my username again. Okay, see if this works. Looks like it did, but just to double check. And you can see, so it looks like this. It's going to put it like this. We can see there's not columns, right? We can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So there are no. This isn't a matrix or a table of values. It's just a list of 1,000 values. Okay, so there's not two columns per se, and it's just one data set. So that might be the first confusing point to get out of the way, is the fact that each of these values is the difference between the desired length of a rod and its measured length, but that's still only one sample of data. Okay, it's not a two sample problem. So well, that would be if we're trying to do like a confidence interval, which is later down the line, I think. But for right now, the goal is just to analyze the data. And so, again, my data is called data. And so I can just copy paste these first 3 lines to get my Weeble maximum likelihood estimates. Just ignore these warning messages. Pull this over here a little bit. So shape goes here, scale goes here, and we can get our QQ plot to see whether the Weeble distribution, okay. Oops, again, if sometimes you might have to click back over here. So we can see that there, right, this looks great right here. The tails, we can see that we have really bad tails, okay, really bad tails. And I'm guessing this should be evident on the histogram as well. So based on just that plot, we'll get to the next one. It's looking like Weeble not looking so hot. So for our next graph is going to be the last 3 lines here, making sure to change our values, and of course Weeble, that's what we're dealing with, so we don't have to change that yet. So here's our histogram, okay? So the histogram to me doesn't look as bad as that QQ plot did, okay? But we've we've got some tail discrepancies that, at least to me, aren't as obvious from this histogram as they are from that QQ plot. Okay, I mean, just looking at it, I mean, that looks decent. Okay, but clearly some discrepancies in that QQ plot that make it more obvious than what we can just visually see personally from a glance at that histogram. Okay, the next one, we want a normal distribution, so we have to get our maximum likelihood estimates for our normal distribution, right? Throw a little hat on top of this, mu hat and sigma hat, right? Mu hat, sigma hat. And here's the one thing we don't want to forget, right? We need to change this to normal now, or norm, right? Can't forget that, or we just did the wrong thing. So, got to take our time when we're doing these and make sure that we're changing the code properly. Okay. This looks pretty bad too. Okay, well, okay. Interesting. So That again looks pretty bad. Let's see what the, oops, let's see what the histogram looks like. Oops. Ah, crap. I accidentally started the line on top of another line, I think. Oops, nope. See, I did do something stupid. Okay, don't forget to change norm, right? Can't forget to change. Okay, this looks very similar to the other one. I don't see much difference between the two so far. So I guess we're gonna have our fingers crossed that this gamma distribution looks better. So we've got our alpha hat and our lambda hat, and we look at it. Actually, oh my goodness. Okay, see? Do what I say, not what I do, right? Q gamma. So sometimes you might, right, it might just kind of be obvious that something went wrong there. And I forgot to change norm to gamma. That's why, see? So I'm rushing myself. Okay. Bad tail behavior. And actually, I was really surprised to see this bad tail behavior on all of the graphs. Okay, and I'm actually going to go back and change something in just a second. Because I actually know that I generated this data from a normal distribution, and with 1,000 observations, I was expecting not to have such a bad looking QQ plot for the normal distribution. Okay, so personally for me anyway, this is the only histogram that looks a little weird, right? The peak just seems shifted here, whereas both these bars look pretty similar. Seems like it should be a little more shifted to the right. So based on just what we've seen so far, I really don't like this, but all of the QQ plots have looked similar, and so I'd probably go with the Weeble and normal. But I'm going to change something. Okay, this code was not designed for sample sizes of 1,000. Okay, I think that this is actually one reason we are getting we're getting bad tail behaviors because because this code needs to be changed a little bit. That's basically the gist of it. Okay, because before we had samples of like 50 or so. I wasn't able to capture with starting at the 2.5 percentile and 97.5 percentile. With 1,000 observations, you will actually see points in those upper and lower percentiles, whereas with an observation of a data set of like 50, you wouldn't. So by changing these, I can adequately capture the fact that I have 1,000 observations, right? 1 out of 1,000, right? 999 out of 1,000. And I guarantee, I'm just going to jump right to the normal. Recall the normal QQ plot looked pretty much just like the other ones, right? They all had bad tail behavior. So let's go back to our normal. And I'm just, I'll look back at the normal and the Weeble because we kind of ruled out the gamma based on this histogram. Okay, so this I'm expecting now to magically, right, we didn't change these numbers, but just basically the way the code was, I'm expecting to have better tail behavior. Okay, and so you can see it looks a lot better than it did, right? We had really bad tail, curving off really bad tail, right? Looks like still a little bit, right? Or in like 1 point up here, but that looks pretty good. Okay, looks like a little bit, not so bad. Okay, let's see what it looks like for the Weeble distribution. That was our first one, Weeble. All right, so this is what we're comparing it against, and here I'll go ahead and remind everybody this is something we can do. Windows, create another window. Sometimes you have to re-click back over here to be able to type again, so don't let that confuse you as to thinking R crashed or something. Okay, so there was the normal, this is the Weeble. Okay, they don't look that dissimilar. I would say there's definitely more happening in this tail than this tail, right? Really, we don't have too much going on except the 1 point. And this here, we're curving away more from the line than this, but here maybe not quite as much. But overall, I feel like there's a little bit more going on with this one than this one, right? Because we almost have another thing we almost have is like all of these points here, for the most part, look like they're on the right side, even though it's not very much, right? It looks like we go from left side, right side, right side, whereas, yeah, we're here, but we're just, see, we're kind of right on the line all in here. And overall, not a whole lot of difference, but I would definitely think, looking closely, that this one is better. Again, the only place this is actually better, all the way up to here, this is better if you look closely. The only place that it's maybe not better is these few points right here. So based on this, I would say to go with the normal distribution to fit this set of data. Now, for the exam, I will try to probably give you a data set that isn't huge, like 1,000 observations, just so that these numbers don't need to be changed. The numbers as they are shouldn't affect the graphs very much when you have a smaller data set. And I'm trying to make you not have to modify the code very much, make it easier. So you shouldn't have to modify these numbers for whatever I give you for the exam. Okay, so we said normal distribution based on mostly the slightly better QQ plot. The histograms looked pretty similar between the Weeble and the normal. So if we wanted the maximum likelihood estimates, right, maybe we had A, B, C, maximum likelihood estimates or something, we can see that we wanted, right, about 4 and about 1. And as I said, this 1,000 observation is actually a sample from a normal distribution that has a mean of 4 exactly and a standard deviation of 1. So we can see, fitting the normal distribution, we were actually able to almost exactly get back those true values because we had such a large sample size. Okay, maximum likelihood estimates, we just said those are the ones that we would pick in R. So we would like to determine if on average they are being produced at the desired length. Okay, so we want a confidence interval. So we want a 90% confidence interval for the average difference between the desired length of a rod and its produced length. Okay, so again, this is where we needed to realize that it's just a one sample problem. And so to be able to determine, right, we're taking the difference, we need to look for 0 because it's in a way kind of like a 2 sample problem, but it's really only 1 sample. It's just the fact that each observation has been subtracted from the desired length, right? So if that interval goes away from 0, we have evidence that they're either being produced too short or too long, right? So should be pretty straightforward. T dot test data. Conf dot level equals 0.9, 90%. And one sample, we just put our sample in there, and that should be all we have to do. Okay. One sample t-test. And so the corresponding 90% confidence interval is from 3.93 to 4.03. Okay, so that conclusion, right, this does not include 0. Let me open up my little window, right? And so what we have, each data point is the difference, just to try to not confuse ourselves, difference between desired length, whatever, we don't even know what that is, and it doesn't really matter. Difference between desired length and produced length. So we can see this entire confidence interval is positive, right? So we are having evidence that there are positive, that this quantity here, difference between the desired length and the produced length on average, is positive, right? So it looks like the desired length is higher than the produced length, which means they are being produced, right, too short. Because when we subtract the desired length, right, some number, subtract off what it's actually being produced at, it's positive. So they're being produced too short. I would say this is one where you have to take the time to think about the problem, because it could be easy to think that they're being produced too long or something if we really don't take the time to think, put things in the right places, right? A minus B, it's completely positive, so this is bigger, thus the produced length is too short. Okay, so of course we did it by hand here, and really, again, you can calculate the sample mean, you can calculate the sample standard deviation. You know there's 1,000 observations. You know alpha is 0.1, so you could calculate QT 0.95, 999, and find this in R, and you could construct this confidence interval by hand, and you would get the same answer, okay? However, I think it's a lot faster to just put t.test data pretty much. Okay. So the assumptions for the interval, right? We assume that we have a random sample just from the wording of the problem, and we've already determined that it looks like a normal distribution is appropriate, or not horribly violated, right? It looks actually good in this case. So the assumptions of the confidence interval are satisfied. So, right, the entire confidence interval was above 0. We have evidence that the difference is positive, and so the rods are too short. Okay. Graphs you could look at if you want to get more exposure. I think, okay, yeah, so ratio of variances, this is not one of the confidence intervals that we have to do, right? Comparing two variances, recall I did not cover this and I did not cover this. You do not have to know these for the exam. Okay, so I'm just going to skip this problem. All right, collected data on the number of defectives. Okay, difference between two proportions. Also don't have to know. Okay, I'm going to skip that. Okay, and that's the end of this exam. Okay. All right, so let's go to exam 2, number 3. Okay, and again, I'll just look at the solutions. I think we've already done 2 of these. Have we done traffic light data? I'm pretty sure we did this. Yeah. Okay, so we've done another similar problem. So we did one of these on the last lecture as well as this one, right? We read in the data, we modify our Weeble analysis code, right? Read in the data with this line, change it a little bit. Right, we need these 2 lines, and then we're going to have to change this for however many distributions we're comparing. Might be a good idea to space things out like this just to see, right, this is what gives us our estimates. We have to have these 2 lines at the very beginning. Again, everything here assumes our data is called data. This, right, we have to modify the 2 parameters, or of course, if we're fitting exponential, there would only be 1 parameter. We have to change the name here. We have to change our estimates, change the name here. These 2 lines give us our QQ plot. These 3 lines give us our histogram with the density curve overlaid. And of course, we have to change the name, recalling that you have to put the full name, gamma, normal, Weeble exponential. You have to put the entire thing here, whereas you might only have to put norm or exp for the normal or exponential. Okay. And so, of course, whichever model we chose, right, the numbers that we're putting in here for the best model, with the one that we believe the best, those are what's called the maximum likelihood estimates. And then usually there's pretty much a separate question about constructing some sort of confidence interval. And we also, on the first exam that we did, so previous lecture, we did a confidence interval for the variance, right? This is one where you have to do it, you have to get these quantities and kind of construct it by hand, right? So we have to just do variance of data to get this, and then we have to do Q, CHISQ for chi-squared. 1 minus alpha over 2, whatever that is, so like 0.995, comma, and then n minus 1, whatever that is, 100, so 99, and then stays the same, and then just put 0.005. So refer to the previous lecture. We did it in a very similar example. Assumptions, so same one, right? Normal distribution, random sample, and standard deviation. But very similar. This problem is very similar to one that we saw in that exam 2, number 1. Okay, here's another one that's not exactly like we've seen before. So we're comparing 2 fuel injection systems. 15 cars are going to receive each system, but in a random order. Below are some of your analyses. Okay, so again, all this stuff you're not going to be given. Instead, you are given fuel. Okay, fuel. It's the one we need for this one. Put it on our desktop. And let's read in the data. Call it fuel. And you can keep it as data. You can change it to fuel because we're not doing a reliability analysis, just a confidence interval. But however you want to do it, let's look at what the fuel data looks like. Okay, so the cars, for system 1, cars for system 2. Right, so we can clearly see we do have 2 samples. However, right, we have to tell which of the 3 methods. We can see we're doing a confidence interval for the difference between the averages, right? So we've got 3 choices. So we have to just simply, based on the wording of this question, determine which of the 3 it is. Well, because 15 cars, so each subject, if you will, receives both treatments. So each car gets treatment 1 and treatment 2, system fuel injection 1, fuel injection 2, and we get a data point for each one. So this is an example of a matched pairs design. So we have dependent samples, so it's that third method. The samples are not independent because each car gets both systems. Okay, so that means looking at the data set, right, this is, say, car 1, and this is its observed value under fuel injection 1, and this is its observed value under fuel injection 2. Of course, I've labeled them A and B, but that's, right, arbitrary, right? Car 2, fuel injection 1, fuel injection 2, right? So each row represents a different car, and so these are matched pairs design, okay? And that's very important to us. So we know now which method to use. We saw from the previous lecture how to do it when we have independent samples. I think in the true example we had different variances, although I did show you how to do it if the variances were the same. Okay, so 94% confidence interval. So to do that, t.test. So this is back to this little trick here, right? This is our first group, this is our second group, okay? So it's called data, and in order to capture this column, right, because this is my first data set, I need to put data, bracket, comma 1, bracket, right? First column, because it's on the right side of the the comma. Oops, sorry about that. Second data set, data, bracket, comma 2, tells it this, okay? Conf.level equals point, what was it, 94, I think. And now, the one thing that we haven't said, before we put like var.equal true or false, that's when we had independent samples, but now we have matched pairs design, so we need to tell it that it is paired, and I believe the argument is paired equals true. Okay, if it gives me an error, then I'll know otherwise. And notice paired t-test. I would always kind of look up, if you do one of the independent samples one, it's going to say something like Welch t-test, but you should still be looking for, variances the same or not, making sure that that's right. But we can clearly see that we did a paired t-test here, and on one of the last examples, we could clearly see it was a one sample t-test. Okay, so 94% confidence interval, 6.2 to 5.6, so 8.6. So see what we're really talking about here. So it looks like, so the average output of a fuel injection system. Okay, average output of a fuel injection system. So, right, we are 94% confident that the average, right, or the difference between the average difference between the mean output of fuel injection system 1 and I'll just put system 2, right, in that order, 1 minus 2, is kind of crappy wording, is between just around 6 and 8.5. Okay, so clearly the entire confidence interval is positive, so that must mean this, right, system 1 had the higher average fuel output, right? And assuming that that's a good thing, then we would have evidence that system 1, fuel injection system 1, is better. Okay. Assumptions of the confidence interval. So technically, because we have dependent samples, we assume that the differences follow a normal distribution. Okay, that's a little bit different, right? When we have one sample, we assume that it follows a normal distribution. When we have two independent samples, we assume that each one follows a normal distribution. But when we have a matched pairs design, we assume that the differences follow a normal distribution. So, of course, I might ask you to actually verify such assumptions. So how could we do that? So again, I'm not assuming A has a normal distribution and B has a normal distribution, but I'm assuming that A minus B has a normal distribution. So, right, 31 minus 21, 31 minus 22. Okay, so what we can do, I'll just call it diff. Okay, diff is equal to data 1, right? That's how we get our first column, minus data 2, bracket, comma 2, bracket, comma 1. Okay, bam, diff, 15 differences. And just to kind of, right, look up, 31 minus 21, right, 31 minus 22, a little more than 22, right? So we can see that each of these data points is now the difference between this one and this one, this one and this one. And that's what we wanted. So we want this to have a normal distribution. So QQ norm diff. Okay, there it is. QQ norm diff. And that looks pretty darn good, especially for a sample size of 15, right? That looks, the differences look normal. Okay, so that's how we verified that the differences were normal. Okay. All right. And we've already said, yes, we have evidence that system one has a higher mean because the entire confidence interval is positive. All right, comparing proportions of two defective items. Again, we're not doing two sample proportion confidence interval. Okay, so it looks like on none of these exams I had an example of a proportion confidence interval. So I'm just going to make one up now. All right, so here's a question. We have 100 parts. 10 are defective. We want a 99% confidence interval for the proportion of defective items. Okay? And that could be the question. So to do that, it's very easy. We have, and now this is the one where if you do this by hand, you might actually get a slightly different answer. I showed you what I believe to be a pretty good example of that in class. So prop.test, and we have 10 successes, right? 10 type 1s, which we're just calling defectives, out of 100 items. Conf.level equals 99%. Bam. Okay. And you can even kind of see, right, 10 out of 100. And right, that's what we had, 10 out of 100. So the 99% confidence interval is 4 to 21, right? So 99% confident that the proportion of defectives is between 4 and 21%. Just be nice and quick about it, 4 and 21%. Okay. So, how about assumptions? You might not remember this one. So, surely we want a random sample. But unlike just about everything else we've talked about, we don't want a normal distribution, right? So that's the go-to answer, and I'm certainly going to put that as an option that I'm sure a lot of people that quickly go through the exam or haven't studied properly will choose. Okay, recall we're talking about defective versus not defective. So if numerically you could just think about this as a 0, meaning it's not defective, and a 1, meaning it's defective. Zeros and ones binary outcomes cannot possibly have a continuous bell-shaped curve. It's going to be, right, 2 bars on a graph. So that can't possibly have a normal distribution. So the assumptions are that we have basically 15 successes and 15 failures. And if you recall, I said that we can put that as n times p hat is at least 15, and n times 1 minus p hat is at least 15, but this is really what it means, 15 successes, 15 failures. So we can see, actually, with a sample size of 100 parts, we still don't have enough, although, well, you know, really this 15 successes and 15 failures, this is more important for the crappy confidence interval that we teach you by hand because it's so terrible. This confidence interval that we do in R is actually a lot better. So really, we don't need this so much, but nonetheless, I'll just stick with that, not trying to confuse things. So just based on this anyway, we might want more, but this confidence interval is a lot better than the one by hand, so really I would be fine using this confidence interval. So for some of the other ones, all of the confidence intervals about the mean, right, we always assume that the data is normally distributed. One of the things that they kind of say is, right, for larger sample sizes, the things work pretty well, and that's usually pretty true because of the central limit theorem. A lot of times they say samples of 30 or more, that's when the normality of the data might not become quite as impactful. Okay, but in general, the true assumption for the confidence intervals for the means is that the data is normally distributed. If you hear people talking about the larger sample sizes, again, that's because of the central limit theorem. When we have large sample sizes, some of these statistics that we're using start to roughly follow normal distributions anyway. Okay. So if we had a question, the proportion of defects has to be 10% or lower, right? Want 10% or lower defect rate. So if this is what we want, our conclusion based on our confidence interval is that we don't have enough evidence, right? Our confidence interval is from 4 to 21, right? 4% to 21%, which includes 10%. So we do not have evidence that there are more than 10% defectives, and we also don't have evidence that there are less than 10% defectives, okay? So inconclusive. All right, I think that's pretty much it for that. Okay. Okay, another ANOVA example here. Well, we've already seen an ANOVA example. So I think battery, electricity, fuel. Okay, I think we've gone through all of these examples, either this lecture or last lecture. So I'm not going to read in another ANOVA example, but to read it in, right, we need our ANOVA and regression code, And again, all of this stuff under regression, right, we don't need for this exam. This is what you need here. And just really pay attention to the last lecture, right? Sepal width, right? That was our variable of interest, right? So that was like lifetime, okay? Species, that's the categories, the different species. Well, now we have different categories of batteries, right? 1, 2, and 3 from the previous example. And so this is how we get our ANOVA table. And the only thing we're really concerned about is the p-value, right, at the end of the table. Make sure you look at the last lecture. And then again, always replacing the variable that we're interested in with whatever it's called. And this with the number of categories, we can do a box plot because one of the assumptions of the ANOVA is that we have equal variances for each group, and we can kind of look at the how wide the box plots are to verify that. We also assume that they're independent samples, random samples, and the other one is that each group is normally distributed. So for the each group is normally distributed, right, that's where we have to modify this one. Basically just replacing each of these with whether it was the variable that we're interested in or the variable that gives us the number of categories. And then of course this title here is useless. You could replace that if you wanted to for each group, say right, 1, 2, 3, etc. And if you recall, pay attention to the last lecture, I think we had to do something like as dot factor on our battery types, maybe up here, maybe down here. Maybe I think it was up here, okay? Because we had battery types listed as 1, 2, 3, it wanted like words, so we had to put as dot factor to get it to work. Please pay attention to that, right? Or if I put an example that has the categories listed as 1, 2, 3, and you just plug and chug, you're not gonna get anything. You're gonna get an error, and not know what to do. Okay. And so before we get to this one, right, when we put this in, we look at the far right hand side to see that probability greater than f, which is again our p-value, and which is over here labeled as p-value, but it's going to say like probability greater than f, some weird thing, but the number is the p-value. And so to get a conclusion, right, we're testing the null hypothesis that the mean lifetimes, in this case of batteries, of 4 batteries in this example, are equal, and the alternative is that the mean lifetimes are different. And so to come to a conclusion in this case, right, we can see that the p-value, 0.068, is greater than alpha. So our conclusion is that we fail to reject the null hypothesis that the means are equal, and so we do not have evidence that there is a difference in the mean lifetimes, right? It's not that we have evidence that the mean lifetimes are equal, it's that we do not have evidence that they are different. And so your choices are gonna be, that you fail to reject the null hypothesis, just exactly like this. I might put the exact same thing, but you reject the null hypothesis, right? So that if you don't understand whether you're rejecting or failing to reject the null hypothesis, and I can change this from we have evidence and we do not have evidence, right? So you really need to understand that we're rejecting the null hypothesis, we're failing in this case to reject the null hypothesis, so that we do not have evidence, okay? Because I could also put we fail to reject the null hypothesis and we have evidence that there's no difference, right? Which is wrong. This is right. So okay, and in the example from the previous lecture, we had a very small p-value less than our significance level alpha, and so we rejected the null hypothesis and we had evidence that there was a difference. Okay, and so in this case, there is no need to perform pairwise comparisons because we don't have evidence that there's a difference, so there's nothing to look for. Okay, and as for the assumptions, right, I just stated what all the assumptions are, and you can produce a box plot like this with that one line of code to verify the equal variances, and of course use that other line of code to verify normality. And of course, you have to do this for each group, right? You have to, this should be the same, but you are going to have to change the group labels each time to get a QQ plot for each group. So this is the line of code, right? Of course, changing our two variables. This is what gives us those pairwise comparisons. Again, refer to the last lecture, that allow us to tell whether if we can order the means, right? If we can tell this one has the biggest mean, this one has the second biggest, this one has the lowest mean, or sometimes we can't tell, we can't order all of them, we can only order some of them, and that's where we're looking at whether those confidence intervals include 0 or not. I did a pretty thorough example last lecture, so really pay attention to that. But in this case, there is no need to do that because we have a high p-value and we failed to reject the null that the means are equal, so we don't have evidence that there's a difference. So there's nothing to look for. If we had rejected it like we did last time, we would do the pairwise comparisons, and that's when we would use this line of code. All right, I think that's pretty much it for what I wanted to do for review. So I really hope you take the time to try to understand everything we talked about, work through it, yourself as I went along, I hope, so that when the test comes, you're prepared to go through it all, right? You have each of those tests, understand, quick thing, I guess, here. Right, we did the t dot test, right, for means. T dot test, right? So there's a lot of different ways that we use the T dot test, right? For one sample, we just did T dot test and basically whatever our data set was called, and maybe conf dot level equals, whatever, 0.9, right? Whatever we want here. If it's 0.95, 95%, you don't even have to bother with this. You can just put T dot test data, okay, assuming whatever your data set's called. Okay, so for two sample, right, we still use T dot test, and we're basically going to need to put basically group 1 comma group 2, okay? The difference is if these are stored in a matrix, which is commonly how I give it to you, you might have to put something like this. So I'll just put it like this: data comma 1, first column of my data set, second column of my data set. Okay, and then there's lots of different ways. How about independent samples equal variance? Okay, I believe it was var dot equal equals true. Okay. Two sample, right, not equal variances. Var dot equal false. Okay. Third way, two sample, right, not independent. Dependent samples. So this useless. Paired equals true. And one thing you should notice, especially between here and here, that title at the top, right, should be a little bit different, right? Paired t-test, one sample t-test. For these, it's probably going to say Welsh two sample t-test, okay? But that's the basic gist. Of course, for each of them, conf.level might have to be changed unless it's 95% confidence. Let's see here. So that's for the mean. So for the variance, right, this didn't have a nice code. You just have to rock that out yourself with this. Okay, for proportions, where am I? Okay, proportions. Prop.test, I'll just put it like this: number of successes, comma, number of trials, right? So, and then of course you might have to change the confidence level. As always, it looks like comp.level. And so this is like, right, if we had 10 successes, I would just put 10. If you have 100 trials, comma 100, right? Just like we did in our example today. Just put the number and the number, whatever that is. You don't put the pound sign. So it would be like prop.test 10, comma 100, whatever the number of successes, right? Successes, again, being a generic way of saying it, could be failures, right? Okay. Okay, we already went through these, right? And we're not doing those. So that, I guess that's for the confidence intervals, right? Those are the main functions that we need. Um, maybe I'll go ahead and save that and send that to you just to make it a little easier. Okay, yeah, I'll send that to you. And of course, for the Weeble analysis code, like I say, maybe it would be helpful for you to kind of separate it like this. Hell, maybe even get rid of this, right? That's not useful to you. I don't know why it's not, oh, hitting the wrong button. Okay, right, separate it like that maybe, just to kind of see each of the pieces where it needs to be, right? Don't forget about that. So again, we have to change our distribution, and we have to, based on what the maximum likelihood estimates are, we have to change the numbers here and here. And we use these two graphs to determine which distribution seems to model the data the best. Okay, and so we can also answer probability. Like once we create this model, didn't really do a whole lot with it, but usually once we create this model, we can start to answer questions like what's the probability, that the variable is greater than this or between these two values. And we can use our model to determine that, right? If we determine that a normal distribution fits the data the best and has, the two parameter values, we can start to put like, right, p norm, less than 10, p norm 10, and then put the two parameter values, and then we get our probability questions answered. So for the ANOVA, again, all of the regression stuff I completely ignore. All we need are these few lines of code, and this is what gives us our table. And the box plot, right, to check the variances is here. The QQ plot to check the normality is here. Recalling we have to change and do however many groups we have, right? ANOVA, we're comparing multiple means. That was the gist of ANOVA. And so for each group, we have to put, right, we have to do a QQ plot for each one, right? We want to see that each group is normally distributed. As I said, p-values here, that's how we come to a conclusion about rejecting the null, failing to reject the null, and what that means. This is for if we do reject the null, we have evidence that the means are different. This is what allows us to see which groups have higher means, lower means, etc. And we do that based on whether the confidence intervals include 0 or not. Okay, refer to the last lecture. And of course, make sure you understand how to do the Weeble questions, right? The actual calculus. I can probably going to ask you a question about the Weeble distribution, right? You might have to use its hazard function. We saw a couple exams, one yesterday, one today, that had a Weeble data question. So you may have to do integrals. Since I didn't really talk about it in this review session, I'll probably, for the Weeble distribution, I'll probably just ask straight probability questions. I'm not going to do the questions about the means. If you recall, for the Weeble distribution, in order to calculate its mean or one of its moments, you not only had to do the U substitution, but you had to use that gamma function trick. And I didn't take the time to go over that gamma function trick again. It's been so long. I won't quiz you on that. So it may be like these two previous exams where I ask you probability questions, but I won't ask you moment questions, so you don't have to remember that gamma trick. All right, I think that's pretty much everything that I wanted to go over. I'm going to send you this and test. My goal is to have it automatically upload to Blackboard at 8:30 and automatically close at 9:45 next Tuesday. Okay, next Tuesday, the 31st. Okay, you have all the tools at your disposal. I would highly recommend before you click start on the test, since it's timed, that you go ahead and get all of your stuff ready. You open R, you have your codes up, right? You have your formula up, you have your lecture notes up, previous exams, whatever you think you might need. That way, once you click start, you're ready to go and you can answer the questions. If there's something that you're still confused about, feel free to email me before the test, and I will do my best to answer it. So good luck to everyone for next week.